This is a tutorial reviewing the concept of VSEPR theory and how that affects molecular shapes. VSEPR stands for valence, let's try that again, valence shell electron pair repulsion theory. So let's review for a minute. Let's go back and look at the periodic table and ask ourselves, how do we know how many valence electrons an element has? Well, if you remember our tutorials about how the periodic table is organized, you realize that the group number is what determines the number of valence electrons each of the elements has. Well, VSEPR theory relies on the fact that electron pairs repel each other. So let's remember that opposite charges, plus and minus, attract. Identical charges, either minus minus or plus plus, repel each other. The goal of VSEPR theory is to construct a geometry that minimizes the repulsion energy as we're forming molecular bonds. Well, repulsion energy, where we're looking at two electrons repelling each other, what law governs that? Well, that of course would be Coulomb's law. If you don't remember the formula, please go back and review it. Our goal is to minimize the overall molecular energy by minimizing the repulsion of the electrons used in forming our bonds. The universe always favors low energy or more stability in the molecules it forms. This minimization of repulsion, which minimizes the energy stored in the molecule, determines the molecular shape. If you haven't heard it from me before, energy is the reason for everything. Well, there are some diseases that are actually caused by issues with molecular shape. Can you think of one? Well, I'll leave that until the last slide, and then we'll review that concept. We're going to start out by reviewing how to write Lewis structures. To write a Lewis structure, we're going to always count the number of valence electrons, not core electrons. We're going to try to pair them together in chemical bonds until we've reached an octet around each of the atoms, or a duet around hydrogen. Shared pairs of electrons are pictured between the atoms that are bonded. Lone pairs of electrons are pictured on the original atom. And of course, sometimes we don't reach a full octet, and that can end up giving us very reactive molecules. We're going to define something called an electron group, which for us is a lone pair of electrons not used in bonding, or the first pair of electrons used in bonding and the first only. Double bonds will count as a single electron group. Triple bonds will count as a single electron group. It turns out that chemical reactivity in many chemical and physical properties are affected by the molecular shapes we're going to describe in this tutorial. Now, here's a question going back to our original discussions about Lewis structures. Do Lewis structures actually tell us anything about geometry? Well, if you remember the discussions we had around Lewis structure, we tried to point out that Lewis structures are not reality as far as the molecules are concerned. They're a convenient way to keep track of the geometry, not geometry, but to keep track of the number of electrons involved in a molecule. But they do not reflect the reality of the shape of the molecule or how it's constructed. Well, let's consider for a minute what molecular shapes we could propose that would maximize the distance between electron groups that are being used either for bonding or for non-bonding electron pairs. Well, let's start out simply. We'll start out with two groups of repelling electrons. So that's our group is going to be 2 electrons apiece. We'll pick some generic element X and see what the geometric arrangement is that will give us the most separation. Well, I could draw an arrangement like this where I've got 90 degrees between my repelling electron pairs, but I think I can probably do better than that. As I move those electron pairs away from each other, I can go to 120 degrees. That's clearly going to be farther away than the 90 degrees that I had. But of course, I can do better. Finally, the farthest apart I can get those 2 repelling electron pairs is 180 degrees apart. Well, beryllium chloride would be an example of that. Or if we want to go to an organic molecule, one that includes double bonds, carbon dioxide also would be included in that group. Now, carbon dioxide, we have carbon oxygen double bonds, but we only count the first pair of electrons in our repelling groups, and that gives us a linear structure. Well, let's move on to three electron groups. Well, I could initially propose a structure that looks like this T shape, where I've got 90 degrees between some of the groups and 180 degrees between the other. But I can probably come up with better geometries than that. We could look at this type of T. Of course, you should recognize all I've done is taken the original structure and rotated it 90 degrees. I still have the same distance between electrons. If I want to maximize the distance between three repelling groups of electrons, I'm going to end up essentially with a structure that looks like an equilateral triangle. I'm going to have 120 degrees between all of those electron pairs. Well, an example of a molecule that looks like this would be aluminum chloride, where we have aluminum, three valence electrons, sharing a valence electron from each of the chlorines, given a grand total of 6 electrons out of the aluminum, around the aluminum. You'll notice, of course, that we have not filled out an octet on the aluminum. We could take a look at another simple organic molecule like formaldehyde, where we've got two carbon-hydrogen single bonds. We have a carbon-oxygen double bond, but only the first one counts. Three repelling electron groups. I would set up in more or less in an equilateral triangle with that structure and 180 degrees between the bonds. Well, what happens if I have four repelling electron groups? Well, I could arrange those four repelling electron groups so that they're 90 degrees apart. I could try to rotate that in space, but no matter what I do with that, all of the electron groups are 90 degrees apart. Is there a better geometry I can come up with that's going to give me more distance between those repelling electron pairs? Well, if I pop that molecule from a flat structure into three dimensions, a three-dimensional structure called a tetrahedron, in fact, I can get those electron groups farther apart. So let's take a look at a minute at the image that we've got here and understand the formalism on how we're constructing this image so that we're trying to convey three-dimensional information on a two-dimensional piece of paper or a flat computer screen. Whenever we see a solid line, that's a chemical bond that's in the plane of either our paper or our computer screen. If we see an elongated triangle that's completely colored in black, that's a chemical bond that is projecting out of the computer screen towards the viewer. And then finally, if we have an elongated triangle that's got cross hatches on it, that's a chemical bond that's projecting behind the computer screen. So in this case, in this tetrahedron, we have two bonds that are in the plane of the screen. We have one bond that's projecting out of the screen, and we have one bond that's projecting behind the screen. Well, we've gone from our first two cases that are flat, two-dimensional molecules, into a molecule that for the first time pops up into three-dimensional space. The easiest example of that is going to be methane, where we have a carbon atom that's bonded to four individual hydrogen atoms. Carbon now has 2, 4, 6, 8 electrons around it, so we've reached an octet. Each of the hydrogens is sharing 2 electrons and has finished its n equals 1 principal quantum shell, so is done acquiring electrons. Well, let's move on to 5 electron repelling groups. I could try to do that in a two-dimensional shape. And if my high school geometry serves me correctly, I believe that's 72 degrees between those repelling electron pairs. I could try popping that up into three-dimensional space. In this particular diagram, I've got 4 repelling electron pairs that are forming a square, which is perpendicular to the surface of the computer screen. And then I've got 1 electron pair that's popped up above that square in a square pyramid structure. But it turns out I can actually move those around and find a different geometry which will give me better separation. In this figure, I've got three electron pairs that form a triangle. That triangle is perpendicular to the computer screen. And I have an electron pair above and an electron pair below that triangle. And we would refer to this as a trigonal bipyramid. It should be noted in this type of molecule, not all positions are created equal. The positions that are in that triangle are 120 degrees away from each other, whereas the repelling electron pairs that are on the top or the bottom pyramid are 90 degrees away from the three repelling electron pairs in the triangle. An example of a molecule with this structure would be arsenic pentafluoride, shown here. Finally, we can consider six repelling electron groups. Again, I can try to do that two-dimensionally, but that's probably doesn't make very much sense. If I pop that into 3 dimensions, I can end up with a structure that looks like this. I have a square defined by 4 of those repelling electron groups. That square is perpendicular to the computer screen. I have a pair above and a pair below that square. So I have a square with a pyramid above and a pyramid below. A sulfur hexafluoride is an example of a molecule that has this geometry. Well, if we were going to summarize molecular geometries in a table, we would take a look at the number of repelling electron pairs we have, the shape that we end up with, and an example of the molecule. So 2 repelling electron pairs, the molecular shape will always be linear. My easy example would be carbon dioxide. 3 repelling electron pairs, trigonal planar. There are plenty of examples of this. Boron trifluoride is one of them. And you'll notice in the examples that we give for the easy examples for trigonal planar, they're group 3 elements of elements like boron and aluminum. They have 3 valence electrons. They tend to form just 3 bonds and then stop reacting. 4 repelling groups would be tetrahedral. We've already looked at methane as an example of that. 5 repelling groups would be trigonal bipyramid. We have a triangle perpendicular to the plane of the screen and a pyramid above and a pyramid below the triangle. Phosphorus pentachloride would be an example of that. And then finally, 6 repelling electron pairs, kind of head-scratchingly, is called an octahedron. Well, octa is 8, but we have 6 repelling pairs. Well, it turns out if you draw the molecular shape for sulfur hexafluoride, and then form the solid geometric shape around that. So I've got a square with a pyramid above, a pyramid below. It turns out that that solid geometric shape has 8 surfaces and thus an octahedron. Well, none of the examples that we've looked at have non-bonding electron pairs. What happens to these geometries when we end up with non-bonding electron pairs around the central atom? Well, let's take a look at some examples of that. When we're worried about lone electron pair geometry, we find that the geometry is determined by the number of electron groups around the central atom. Well, let's go ahead and count those electron groups. Each of the following counts as 1 electron group. A single lone pair of electrons, a single bond or triple bond or double bond counts as 1 repelling electron group. Even a single electron, a class of molecules that we've learned to call free radicals, a single electron also counts as a repelling group. Well, the energy of repulsion for those different types of groups looks something like this. If I have 2 lone pairs that are repelling each other, that's going to be the largest of the energies of these electron groups repelling each other. A bonding pair and a lone pair repelling each other will be next largest, and bonding pair will be the smallest. As we go to arrange our geometries, we're going to have to remember that the largest repulsion is lone pair, and we will need to assemble our geometries to minimize that repulsion, all the way down to the smallest repulsion, which is bonding pair. All right, so lone pair electrons, electron geometry versus molecular geometry. So obviously some of our electron pairs are not associated with bonds. We refer to these as lone electron pairs. Well, in any given molecule, how are we going to determine how many lone pairs that we have? Well, of course, we're going to draw our Lewis structures first. That's why it's so important for us to be able to build on a solid foundation of the understanding of Lewis structures. And then we'll start to consider our geometry. Well, if we understand that lone pairs are more repulsive than bonding pairs, how is that going to show up as we look at geometry? Well, we'll go back and start out with our simplest three-dimensional shape, which is a tetrahedron, and our simplest molecule, which is methane. Methane is a perfect tetrahedron with actually it's 109.5 degrees angle between the individual carbon hydrogen bonds. That's the farthest away those repelling electrons can get. Well, if I take a look at carbon in the periodic table and move one to the right, I find nitrogen. Well, if I form the corresponding molecule from nitrogen and hydrogen, I get ammonia. Now, the difference between carbon and nitrogen has one more electron. That electron is spin paired with one of its other valence electrons. So nitrogen has one non-bonding electron pair. Because the non-bonding electron pair is more repulsive, it's pushing down on those bonding electron pairs that are holding the nitrogen and hydrogen atoms together. As a result of that, the geometry between my nitrogen hydrogen bonds has been compressed, and I've dropped from 109.5 degrees to 107 degrees. So now we see the practical effect of this lone pair repulsion. Well, if I was going to continue drawing molecules in this series, take a look at the periodic table and tell me which molecule am I going to look at next. Well, if I went from carbon to nitrogen, one to the right in the periodic table, if I go one more to the right in the periodic table and substitute oxygen in as my central atom, I end up with water. Water now, instead of having one lone pair of electrons, has two lone pairs of electrons. These are more repulsive than our bonding pairs. They're going to squeeze down those oxygen-hydrogen bonds and force them even closer together than we had for ammonia. So we can see this clear pattern, 109.5, 107, and 104, as we look at the angles between those bonds. Well, we're going to make a definitional difference between electron geometry and molecular geometry. And you'll need to be able to understand these if you want to understand how our molecular geometries are formed. So the first thing that we're going to do using our Lewis structures is we're going to locate all of the electrons, all of the electron pairs. So if we take a look at the electron geometry around methane, we see that there are four pairs of repelling electrons. That gives us a tetrahedral structure. And the electron geometry of methane is tetrahedral. Now we're going to locate the atoms and see what the molecular geometry is. If we locate the atoms in methane, we see the atoms are in exactly the same positions as the repelling electron pairs. The molecular geometry for methane is the same as the electron geometry for methane. They're both tetrahedral. Well, let's go ahead and repeat the exercise for ammonia. Ammonia still has four repelling pairs, which makes the electron geometry tetrahedral. But now if we look at the location of the atoms, one of those repelling electron pairs doesn't have an atom. And now the molecular geometry is different than the electron geometry, and we would refer to the molecular geometry for ammonia as a trigonal pyramid. Our hydrogens form a triangle. We have a nitrogen at the top of the pyramid, a trigonal pyramid. Again, we move on to water. The electron geometry is still the same. We've got four repelling electron pairs, which is tetrahedral. And if we take a look at the molecular geometry, only taking a look at the location of the atoms, we see, in fact, the molecular geometry is bent. If we draw a line from hydrogen to oxygen back down to the other hydrogen, we end up with a bent line. So we refer to the molecular geometry of water as bent. Okay, so what this tells us is if we have no non-bonding electron pairs, the electron geometry and the molecular geometry will be the same. If we have non-bonding electron pairs, we need to figure out how many, because they will affect the molecular geometry of the resulting molecule. All right, so let's review the steps that we're going to go through to determine molecular geometries according to VSEPR theory. We're going to go through the following steps. We're going to ask ourselves, how many electron groups are around the central atom? Well, we'll arrive at the answer to that by drawing our Lewis structure. We're going to then find the corresponding electron pair geometry. 2 is linear, 3 is trigonal planar, 4 is tetrahedral, and on and on. That will be our electron pair geometry. We'll then go back to our Lewis structure and say, do we have any non-bonding electron pairs? And if we do, how many do we have? We're going to place those non-bonding electron pairs in the positions in the geometry that minimize their interaction with other electron pairs. If you haven't heard it before, energy is the reason for everything. We're trying to minimize the energy inside of the molecule. Once we've located the non-bonding electron pairs, we will then locate our atoms in the remaining positions. And then looking only at the atoms, not including the non-bonding electron pairs, we will determine the molecular geometry. So just to review then, the electron and molecular geometries will be different only if we have non-bonding electron pairs. Well, let's go ahead and walk back through some of those examples that we looked at. We'll take a look at molecular geometries that now include non-bonding electrons. It turns out if we only have 2 repelling groups and we replace, and one of them is a non-bonding pair, the molecule is still linear. It only has 2 atoms. So we'll pick up with 3 electron groups, which will always give me an electron geometry that's trigonal planar. Well, the example we looked at was aluminum chloride, where aluminum has 3 valence electrons. It shares those in 3 bonds, trigonal planar. But we can also look at a molecule like sulfur dioxide. Sulfur dioxide, 3 repelling electron pairs, which makes the electron geometry trigonal planar. But if we draw a line between the atoms, we see that the molecular geometry is bent. Again, we go to 4 repelling groups, which is always tetrahedral for electron geometry. Methane is the example we used initially. If we take a look then at ammonia, 4 repelling electron groups, but 1 non-bonding electron pair, we have a trigonal pyramid. Oxygen, an electron geometry of tetrahedral, but if we look at the atoms, we see that water, in fact, is a bent molecule. We'll go to 5 electron groups, which is always a trigonal bipyramid for electron geometry. Arsenic pentafluoride has no non-bonding electron pairs, and the molecular geometry is the same. But as soon as we start to incorporate non-bonding electron pairs, as we see here in sulfur tetrafluoride, we now get a different geometry. And we would refer to this geometry as a seesaw after a piece of playground equipment, which my generation got to use, and younger generations probably never saw because of lawsuits. We can move on to two non-bonding electron pairs for bromine trifluoride, and you can see that the molecular geometry is T-shaped. Now, when we have 5 repelling electron groups, we have positions that are not equivalent. The positions in the triangle are not equivalent to the positions in the pyramid. And as you can see, as we start to put our non-bonding electron pairs into the structure, our non-bonding electron pairs always preferentially go into that triangle because they're 120 degrees away from other repelling electron pairs as opposed to 90. So our seesaw, we've got our first non-bonding electron pair has gone into one position in the triangle. Boron trifluoride, our second electron pair, 120 degrees away from the first non-bonding electron pair. And then finally, an example of 3 non-bonding electron pairs would be triiodide. You'll notice that this molecule is actually charged. It's an anion. And our three non-bonding electron pairs have occupied all of the positions in the triangle. So our molecular shape now, looking at the position of the iodine atoms, our molecular shape is linear. Let's go through one more of those. Six repelling electron groups, always octahedral, no non-bonding electron pairs. Sulfur hexafluoride would be an example. Now here we've got all of these positions are equal. As we put in our first non-bonding electron pair in bromine pentafluoride, we can see we now have a molecular shape that's a square pyramid. We've got four fluorines in a square perpendicular to the screen, and one fluorine in a pyramid apex above that square. If we go to put in one more non-bonding electron pair in this structure, though, now the positions are no longer equivalent. In fact, the second non-bonding electron pair will go in the position that's farthest away from the first one that went in. So we've got our non-bonding electron pairs above and below the square formed by our fluorine atoms. So xenon tetrafluoride, in fact, would be square. All right, let's just initially take a look at something that's related to molecular structure, which is polarity. We get the concept of polarity by combining the geometry we've just reviewed with our knowledge of a quantity called electronegativity. Electronegativity is the tendency for an atom in a chemical bond to draw electrons towards itself so that the electrons are no longer evenly distributed between the two atoms that are bonded. All right, so we're going to start out looking at a simple atom like methane, and I have conveniently popped up a chart here which has the numeric values for electronegativity. Well, our carbon-hydrogen atoms, if we take a look at the electronegativity values, we find that they're relatively close to each other, 2.5 versus 2.1. And if I calculate the difference in electronegativity, I've got 0.4. The little triangle you see here is the capital Greek delta, which we use to represent differences. So the difference in electronegativity here is 0.4. That's close enough to those electrons being exactly in the middle of the bond that we judge carbon-hydrogen bonds to be nonpolar wherever we see them. Okay, nonpolar, which means we don't have a charge distribution inside of the molecule. Well, what happens if we replace one of those carbon-hydrogen bonds with a carbon-fluorine bond? Well, let's locate the electronegativity value for fluorine in our table. It is 4. Now, if I take a look at the differences in electronegativity between fluorine and carbon, it's 4 versus 2.1. Well, what that tells me is in that chemical bond, my electrons have a higher probability of being found closer to the fluorine and a lower probability being found close to the carbon. That gives me a partial positive charge and a partial negative charge across that bond. So the symbols we've got here now are small Greek deltas, indicating we don't have a full integer value there, -1 +1. We've got a fraction of -1 +1. And again, if we want to show our electron probability cloud, we see that that's going to be pushed towards the fluorine. Well, let's go ahead and draw that molecule now. So this would be fluoromethane, shown here. My difference in electronegativity is 1.5. I clearly have a charge separation, a partial plus charge on the carbon, partial negative charge on the fluorine. So my charge is asymmetrically distributed as opposed to symmetrically distributed, and the molecule would be polar. And if I went ahead and calculated a dipole moment and gave myself the symbol that we use for dipole moment, it would be this angle, this arrow, starting out at the center of my positive charge, carbon, with the arrow pointed towards the center of my negative charge, which is fluorine. Well, let's continue along this substitution and substitute in another fluorine for hydrogen. Again, I'm going to have partial positive and partial negative charges. Both of the fluorines will be partial negatively charged. The carbon now much more positively charged than in the previous example because I've got two fluorines that are pulling electron density away from that carbon. Well, if we're trying to determine the dipole moments for this molecule, we're going to have to average the geometric location of those two partial negative charges. That puts my average negative position somewhere between those two fluorines. And now, when I draw the vector for my dipole moment, it still starts at carbon, but it points to midway between the two fluorines. Well, let's hurry along to the kicker here, where I have now synthesized tetrafluoromethane. All right, so I have four carbon fluorine bonds, all of which are very polar. I've got partial negative charges on all of the fluorines. I've got a huge partial positive charge on that carbon. If I calculate the difference in electronegativity for each one of those bonds, I come up with 1.5. But for this particular example, if I take the average geometric location of those four partial negative charges, because the molecule is symmetric, the location of the average location of those negative charges is in exactly the same position on the carbon as the average positive position in the molecule. So although I have four polar bonds, the molecule is nonpolar and has no dipole moment. There is no physical separation in space between where my partial positive charge is and the average position of my partial negative charges. Okay, so why would this be important, and why does a concept like this potentially affect some diseases we would be interested in? Well, the importance of molecular shape in biological systems is shown by things like enzymes and antibodies, which recognize their targets based on molecular shape. In terms of diseases, the Nobel Prize in Physiology in 1997 went to Dr. Stanley Prisner, who discovered or pretty much invented the concept of diseases which are caused by molecular shape. Up until the point of Dr. Prisner's investigations, everybody knew to cause a disease, you needed to have some sort of vector or infective agent that had at least nucleic acids. So for bacteria, that's DNA. For viruses, that's RNA. We've got fungal infective agents. We have protozoan. What all those infective agents have in common is they either have DNA or RNA. Well, Dr. Prisner had a patient who suffered from something referred to as Creutzfeldt-Jakob disease, or CJD. And it turns out that there are a number of diseases, both of humans and in the animal world, that are caused by the same thing. So in sheep, it's scrapie. In cattle, it's mad cow disease. It turns out there was a very weird neurologic disease that was endemic in cannibals in the island of New Guinea called Kuru. And all of these diseases, if you go to look for an effective infective agent, you can't find one, as long as your definition of infective agent means that it has either DNA or RNA. And after decades of study, Dr. Prisner finally postulated a disease that was simply protein based and did not have nucleotides. He took, for several decades, he took a beating in the medical community because of these theories. But then ultimately, he won the Nobel Prize because he was right. And in fact, these diseases are caused by the misfolding in 3 dimensions of proteins. So the situation we have is these proteins have been assembled correctly. They have the right sequence of chemical bonds. They have the right sequence of amino acids forming these long chain proteins. But when these proteins go to fold into a specific three-dimensional shape, they misfold into the wrong shape. And as soon as that happens, there are all sorts of problems inside the cells, and in this case, inside of nerve cells, that end up killing those nerve cells. Now, if this concept sounds familiar, it may be because you know a little bit about Alzheimer's disease. Alzheimer's disease is a disease of a misfolded protein called amyloid beta. And it's only been within the last decade or so that people have recognized, in fact, that Alzheimer's disease, whatever the cause, is a disease of misfolded proteins. And the term coined by Dr. Prisner as he was classifying this set of diseases, they're referred to as prions. Prions for proteinaceous infectious particle. So Alzheimer's is a disease of prions. It turns out once you know where to look, you actually can find that these diseases are relatively common. Before I moved to Oregon State, I lived in Wisconsin, a big deer hunting state. And in fact, the wild deer population in central Wisconsin suffers from a very similar type of disease called by prions. It's referred to as a deer wasting disease, but it has exactly the same roots as the ones that we've discussed here, discovered by our Nobel Prize winner.